Reversible reactions. Reversible reactions. Some reactions go to completion, where the reactants are used up to form the product molecules and the reaction stops when all of the reactants are used up. In reversible reactions, the product molecules can themselves react with each other or decompose and form the reactant molecules again. It is said that the reaction can occur in both directions, the forward reaction which forms the products and the reverse reaction which forms the reactants. Chemical equations for reversible reactions. When writing chemical equations for reversible reactions, two arrows are used to indicate the forward and reverse reactions. Each one is drawn with just half an arrowhead, the top one points to the right, and the bottom one points to the left, rightwards harpoon over leftwards harpoon. Example: the reaction for the Haber process, which is the production of ammonia from hydrogen and nitrogen. N2 plus 3H2 rightwards harpoon over leftwards harpoon 2NH3. Hydrated and anhydrous salts. Hydrated salts are salts that contain water of crystallization which affects their molecular shape and color. Water of crystallization is the water that is stoichiometrically included in the structure of some salts during the crystallization process. A common example is copper sulfate, which crystallizes forming the salt copper sulfate pentahydrate, CuSO4.5H2O. Water of crystallization is indicated with a dot written in between the salt molecule and the surrounding water molecules. Anhydrous salts are those that have lost their water of crystallization, usually by heating, in which the salt becomes dehydrated. Dehydration of hydrated cobalt chloride. Hydrated cobalt chloride rightwards harpoon over leftwards harpoon anhydrous cobalt chloride plus water. Diagram showing the dehydration of hydrated cobalt chloride. Hydration of cobalt chloride. When anhydrous blue cobalt chloride crystals are added to water, they turn pink and the reaction is reversible. When the cobalt chloride crystals are heated in a test tube, the pink crystals turn back to the blue color again as the water of crystallization is lost. The form of cobalt chloride in the crystals that are pink is known as hydrated cobalt chloride because it contains water of crystallization. When hydrated cobalt chloride is heated, it loses its water of crystallization and turns into anhydrous cobalt chloride. CoCl2.6H2O(S) rightwards harpoon over leftwards harpoon CoCl2S plus 6H2O(L). Exam tip: the hydration of CoCl2 and CuSO4 are chemical tests which are commonly used to detect the presence of water. You should remember the equations and color changes. CoCl2 plus 6H2O rightwards harpoon over leftwards harpoon CoCl2.6H2O blue to pink. CuSO4 plus 5H2O rightwards harpoon over leftwards harpoon CuSO4.5H2O white to blue. The concept of equilibrium. We have already seen that a reversible reaction is one that occurs in both directions. When during the course of reaction, the rate of the forward reaction equals the rate of the reverse reaction, then the overall reaction is said to be in a state of equilibrium. Equilibrium is dynamic, e.g. the molecules on the left and right of the equation are changing into each other by chemical reactions constantly and at the same rate. The concentration of reactants and products remains constant given there is no other change to the system such as temperature and pressure. It only occurs in a closed system so that none of the participating chemical species are able to leave the reaction vessel. Equilibrium can only be reached in a closed vessel, which prevents reactants or products from escaping the system. An example of dynamic equilibrium is the reaction between H2 and N2 in the Haber process. When only nitrogen and hydrogen are present at the beginning of the reaction, the rate of the forward reaction is at its highest, since the concentrations of hydrogen and nitrogen are at their highest. As the reaction proceeds, the concentrations of hydrogen and nitrogen gradually decrease, so the rate of the forward reaction will decrease. However, the concentration of ammonia is gradually increasing, and so the rate of the backward reaction will increase. Ammonia will decompose to reform hydrogen and nitrogen. Since the two reactions are interlinked and none of the gas can escape, the rate of the forward reaction and the rate of the backward reaction will eventually become equal and equilibrium is reached. 3H2G plus N2G rightwards harpoon over leftwards harpoon 2NH3G. Diagram showing when the rates of forward and backward reactions become equal. Equilibrium position refers to the relationship between the concentration of reactants and products at the equilibrium state. When the position of equilibrium shifts to the left, it means the concentration of reactant increases. When the position of equilibrium shifts to right, this means the concentration of product increases. Le Chatelier principle. The relative amounts of all the reactants and products at equilibrium depend on the conditions of the reaction. This balance is framed in an important concept known as Le Chatelier principle, named after Henri Le Chatelier, who was a French military engineer in the 19th century. This principle states that when a change is made to the conditions of a system at equilibrium, the system automatically moves to oppose the change. The principle is used to predict changes to the position of equilibrium when there are changes in temperature, pressure, or concentration. Knowing the energy changes, states, and concentrations involved allows us to use the principle to manipulate the outcome of reversible reactions. For example, if the pressure is increased, the position of equilibrium moves in the direction which has the smallest amount of gaseous molecules. The position of equilibrium is said to shift to the right when the forward reaction is favored and there is an increase in the amount of products formed. The position of equilibrium is said to shift to the left when the reverse reaction is favored and there is an increase in the amount of reactants formed. The effect of temperature on equilibrium. Table showing the effects of temperature on equilibrium. Example: iodine monochloride reacts reversibly with chlorine to form iodine trichloride. ICl plus Cl2 rightwards harpoon over leftwards harpoon ICl3. Dark brown yellow. When the equilibrium mixture is heated, it becomes dark brown in color. You can use this observation to deduce whether the backward reaction is exothermic or endothermic. Equilibrium has shifted to the left as the color dark brown means that more ICI is produced. Increasing temperature moves the equilibrium in the endothermic direction, so the backward reaction is endothermic. The effect of pressure on equilibrium. Table showing the effects of pressure on equilibrium. Example: nitrogen dioxide can form dinitrogen tetroxide, a colorless gas. 2NO2 rightwards harpoon over leftwards harpoon N2O4. Brown gas, colorless gas. Predict the effect of an increase in pressure on the position of equilibrium. Number of molecules of gas on the left equals 2. Number of molecules of gas on the right equals 1. An increase in pressure will cause equilibrium to shift in the direction that produces the smaller number of molecules of gas. So equilibrium shifts to the right. The reaction mixture becomes paler as more colorless N2O4 is produced. The effect of concentration on equilibrium. Table showing the effects of concentration on equilibrium. Example: iodine monochloride reacts reversibly with chlorine to form iodine trichloride. ICl plus Cl2 rightwards harpoon over leftwards harpoon ICl3. Dark brown.
Yellow. Predict the effect of an increase in concentration on the position of equilibrium. An increase in the concentration of ICl or Cl2 causes the equilibrium to shift to the right so more of the yellow product is formed. A decrease in the concentration of ICl or Cl2 causes the equilibrium to shift to the left so more of the dark brown reactant is formed. The effect of a catalyst on equilibrium. The presence of a catalyst does not affect the position of equilibrium, but it does increase the rate at which equilibrium is reached. This is because the catalyst increases the rate of both the forward and backward reactions by the same amount by providing an alternative pathway requiring lower activation energy. As a result, the concentration of reactants and products is nevertheless the same at equilibrium as it would be without the catalyst. Diagram showing the effect of a catalyst on the time taken for equilibrium to be established. Exam tip: when the conditions at equilibrium are changed, the system always responds by doing the opposite. For example, if the concentration is increased, the system tries to reduce it by changing the direction of the reaction, or if the temperature is increased, the system will try to reduce the temperature by absorbing the extra heat. The Haber process. Ammonia is manufactured in an exothermic reaction called the Haber process, which occurs in 5 stages. Stage 1, H2 and N2 are obtained from methane and the air respectively and are pumped into the compressor through pipe. Stage 2, the gases are compressed to about 200 atmospheres inside the compressor. Stage 3, the pressurized gases are pumped into a tank containing layers of catalytic iron beds at a temperature of 450 degrees Celsius. Some of the hydrogen and nitrogen react to form ammonia. N2G plus 3H2G rightwards harpoon over leftwards harpoon 2NH3G. Stage 4, unreacted H2 and N2 and the product ammonia pass into a cooling tank. The ammonia is liquefied and removed to pressurized storage vessels. Stage 5, the unreacted H2 and N2 gases are recycled back into the system and start over again. The production of ammonia by the Haber process. Exam tip: you need to be able to recall the temperature, pressure and name of the catalyst used in the Haber process. Explaining the conditions in the Haber process. Reaction conditions such as temperature and pressure affect the rate of a reaction. If the reaction is reversible, then the position of equilibrium is also affected by changes in these conditions, and often we must consider a trade-off between the rate of reaction and product yield. The graph below illustrates the effects of changing temperature and pressure on the yield of ammonia obtained. By following any of the curved lines on the graph, it can be seen that as the pressure increases, so too does the yield at any given temperature. By following any vertical line upwards from the x-axis, the graph shows that as the temperature decreases, the yield actually increases. The actual conditions used must be chosen depending on a number of economical, chemical, and practical considerations. The yield of ammonia produced changes with changes made to temperature and pressure. Economic considerations. Like all industries, companies that manufacture and sell chemical goods do so to make a profit. Part of the industrial process is the economic decision on how and where to design and implement a manufacturing site. The availability and cost of raw materials is a major consideration which must be studied well before any decisions are taken. In the Haber process, the raw materials are readily available and inexpensive to purify. Nitrogen, from the air. Hydrogen from natural gas. If the cost of extraction of raw materials is too high or they are unavailable, then the process is no longer economically viable. Many industrial processes require huge amounts of heat and pressure, which is very expensive to maintain. Production energy costs are also a factor to be considered carefully and alongside the raw materials issue. Temperature. 450 C. A higher temperature would favor the reverse reaction as it is endothermic, takes in heat, so a higher yield of reactants would be made. If a lower temperature is used, it favors the forward reaction as it is exothermic, releases heat, so a higher yield of products will be made. However, at a lower temperature, the rate of reaction is very slow. So 450 C is a compromise temperature between having a lower yield of products but being made more quickly. Pressure. 200 atmospheres. A lower pressure would favor the reverse reaction as the system will try to increase the pressure by creating more molecules, 4 molecules of gaseous reactants, so a higher yield of reactants will be made. A higher pressure would favor the forward reaction as it will try to decrease the pressure by creating less molecules, 2 molecules of gaseous products, so a higher yield of products will be made. However, high pressures can be dangerous and very expensive equipment is needed. So 200 atmospheres is a compromise pressure between a lower yield of products being made safely and economically. Catalyst. Iron. The presence of a catalyst does not affect the position of equilibrium, but it does increase the rate at which equilibrium is reached. This is because the catalyst increases the rate of both the forward and backward reactions by the same amount by providing an alternative pathway requiring lower activation energy. As a result, the concentration of reactants and products is nevertheless the same at equilibrium as it would be without the catalyst. So a catalyst is used as it helps the reaction reach equilibrium quicker. It allows for an acceptable yield to be achieved at a lower temperature by lowering the activation energy required. Without it, the process would have to be carried out at an even higher temperature, increasing costs and decreasing yield as the higher temperature decomposes more of the NH3 molecules. Exam tip. The reaction conditions chosen for the Haber process are not ideal in terms of the yield but do provide balance between product yield, reaction rate, and production cost. These are called compromise conditions as they are chosen to give a good compromise between the yield, rate, and cost. The contact process. Sulfuric acid is synthesized by the contact process. Concentrated sulfuric acid is used in car batteries, making fertilizers, soaps, and detergents. The first stage is the production of sulfur dioxide, either by burning sulfur to oxidize the sulfur, equation shown below, or roasting sulfide ores. S plus O2 right pointing arrow SO2. The main stage in the contact process is the oxidation of sulfur dioxide to sulfur trioxide using a vanadium V oxide, V2O5, catalyst. 2SO2 plus O2 2SO3. The oxygen used in this stage is obtained from air. The conditions for this main stage of production are a temperature of 450 C, a pressure of 2 atmospheres 200 kilopascals. Once sulfur trioxide is formed, it undergoes more processes to produce sulfuric acid. Exam tip. You need to recall the temperature, pressure, and catalyst needed for the contact process and the equation for the main stage only. Explaining the conditions in the contact process. Similar to the Haber process, the pressure and temperature used need to be considered. The equation for the main stage of the contact process is 2SO2 plus O2 2SO3. Temperature 450 C. The forward reaction is exothermic, so increasing the temperature shifts the position of equilibrium to the left in the direction of the reactants. Therefore, the higher the temperature, the lower the yield of sulfur trioxide. The optimum temperature is a compromise between a higher rate of reaction at a higher temperature and a lower equilibrium yield at a higher temperature. Pressure 2 atmospheres. An increase in pressure shifts the position of equilibrium to the right in the direction of a smaller number of gaseous molecules. However, the position of equilibrium lies far to the right. The equilibrium mixture contains about 96% sulfur trioxide. So the reaction is carried out at just above atmospheric pressure because high pressures can be dangerous and very expensive equipment is needed. A higher pressure causes the sulfur dioxide to liquefy. Exam tip. Remember, these conditions are a compromise between yield, rate, safety and cost.